R, and then we'll go through some basic sequences and the telescoping technique and a famous sequence. So what are sequences? They're lists of numbers with a certain order that follow a certain rule or pattern. So an example is the sequence of natural numbers, which is 0, 1, 2, 3, 4, dot, dot, dot. Can anyone name another sequence? Just tell me in the chat. Okay, I'll name a sequence for everyone. So another sequence, which is commonly used in Olympiad, is a sequence of odd numbers, which is 1, 3, 5, 7, dot, dot, dot. And there's also the sequence of even numbers, 2, 4, 6, 8. And there's also the sequence of powers of 2, which is like 2, 4, 8, 16. Yeah, this Fibonacci sequence is a very famous sequence. So we call the nth number in the sequence to be the nth term. That's a bit of terminology. And then here are some examples. What is the nth term of the sequence of positive integers? Can anyone tell me in chat? Yeah, Emily, that's correct. It is n. And what's the nth term of the sequence of natural numbers? Can someone tell me in the chat? Okay, so natural numbers start with 0 instead of 1, right? So it should be n minus 1. And what's the nth term of the sequence of negative integers? It's just negative n. So can you guys please guess the pattern for the following sequence? 1, 3, 5, 7, 9. It should be pretty obvious. It's just the odd numbers. Or 2n minus 1. And the pattern for the next one is just 2 to the n minus 1. So we usually denote the nth term of the sequence as an, but it can also be xn, bn, cn, basically anything n. And then usually you're given n plus 1 equals some random expression. It just establishes the relationship between the n plus 1th term and the terms that come before it. So you might get an plus 1 equals an plus 2 or something, or 2an. So there's two ways of defining a sequence. It's the recursive definition, which directly relates an plus 1 to something. And there's also the general formula, which relates an plus 1 to n. So here's your task. Find the general formula for the first sequence.
Hello. I have a question. Oh, yes.
Yeah, I think I made a typo.
Yeah, and the second one as well, maybe.
Yeah,
Cool.
sorry.
I was just going to ask about that. Thank you for clearing it up.
So for the sequence, if you just write out the first few terms, you get the idea that it's 0, 1, 2, 3, dot, 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 which is just the natural numbers. And for this sequence, it's 2 to the n minus 1, right? Because it's 1, 2, 4, 8, dot, dot, dot. So next we'll go through some basic sequences. So the first basic sequence we'll go through is the arithmetic sequence. In an arithmetic sequence, successive terms have a common difference, arithmetic difference. So an plus 1 is just an plus k, where k can be any real number. So here's an example. The sequence of odd positive integers is 1, 3, 5, 7, 9, dot, dot, dot. What is the relationship between an plus 1 and an? Can someone tell me in chat? Yeah, an plus 1 is an plus 2. So what's the general formula for the nth term of the sequence? Yeah, that's also correct. 2n minus 1. So there's properties of the arithmetic sequence, which are very commonly used. The first one that we'll be covering is predictiveness. So Chris will explain this.
Okay. Hello, guys. So the first property of arithmetic sequences we're looking at is, as Alan said, predictiveness. So, what this means is that we want to be able to like predict or know uh, what a general term would be. So, for example, if I give you some kind of arithmetic sequence, can you find the 100th term in it, right? Without calculating the first, second, third, fourth, just knowing the exact value of any general term, right? So a sub n for any n. Um, so an example of this is if we consider the sequence of odd numbers, which is note an arithmetic sequence with starting term 1 and common difference 2, right? 1, then add 2 to get 3, add 2 to get 5, add 2 to get 7, and so on. Let's say the nth odd number is 11,111 and find n. So maybe what you want to do for this, oh, wait, are we like try explain this or should I give them a bit of time to think?
Give them a bit of time to think.
Okay, yeah. Well, we'll give you guys not too much time, but maybe like 30 seconds or a minute to just have a think about this. Does anyone have any ideas on how you might, solve this problem?
Yeah, that's correct. So you could just directly use the formula, which we discovered earlier, to be 2n minus 1, right? Which gives us n equals 5556, I think. But then there's also another approach that we can take. So we know that each consecutive term differs by 2, right? So and we start with 1. So 1 plus 2. And then since it's the nth term, there will be n minus 1 differences from 1, right? N minus 1 equals 1, 1, 1, 1, 1. So that's an alternative route we can take. So yeah. And the second property is the sum of the first n terms. So when we are given an arithmetic sequence, we can always find the sum of the first n terms, and Chris will explain why.
Okay, I got you. Okay. So, okay, the sum of the first n terms. Okay, so a sequence of numbers, right, is remember like some ordered like list of numbers. Here we're dealing with what's called a series, which is like a sum of a sequence, right? So okay, so what we can do is like instead of just giving you the general formula, right? Let's have a look at some small cases, which is obviously always very good to do, right? So if we have our sequence, our arithmetic sequence, which has common difference k, so you add k every time you go to a new element of our sequence, right? New term. And using the fact that the general like nth term of our sequence is a sub 1, so the first term, plus n minus 1 copies of the common difference, right? Because like every time you like advance a term, you add another copy of the common difference. So we're using the fact that a sub n is equal to a sub 1 plus n minus 1 times k. So with that in mind, let's try figure out the sum of the first n terms for a few small values of n. And here we got them nicely listed out. For n equals 2, you see that the sum of the first two terms is 2 times the first term plus k. The sum of the first three terms is 3 times the first term plus 3k. Then the sum of the first four terms is 4 times the first term plus 6k. And you can keep going on. And what you might notice here is that the coefficient in front of the first term is just n. Yeah, so for n equals 5, the coefficient is 5. But the coefficient in front of the k, which is our common difference here, looks to be the triangular numbers, right? It goes from 1 to 3 to 6 to 10. And that kind of makes sense if you look at what we're actually doing, because we're, for example, n equals 5 here, we're adding like k plus 2k plus 3k plus 4k, which comes from the second term, third term, fourth term, and fifth term respectively, right? Because each larger term, you're adding one more. Well, the coefficient from the k gets one larger, so it goes from 1 to 2 to 3 to 4. You sum those up, and you get the fourth triangular number, which is 10. So you have 10k for n equals 5. So for a general n, the coefficient in front of the k is the n minus 1th triangular number. So with those like two facts in mind, I guess we're ready to come up with a general formula for the sum of the first n terms in terms of our variables now. And yeah, it's just this, right? So, right, it's just the triangular number, right? N times n minus 1 over 2. That's the sum of the numbers from 1 to n minus 1. And yeah, that's the general formula. You have n as your coefficient in front of the a sub 1, and you have n times n minus 1 over 2 as your coefficient in front of your difference k. Okay, so using this formula, we have our next question, which is just to find the sum of the first n natural numbers with a sequence of, isn't natural numbers typically not including 0? Or
Oh, I just include 0.
okay, well, yeah, sure. We can call them whole numbers or just natural numbers including 0. That's fine. So the sum of the first n natural numbers, where the natural numbers is 0, 1, 2, 3, 4, and just all the positive integers after that.
So to do this, we could just plug in values. So we know that a1 is simply equal to 0, right? And then the common difference is just 1. So k equals 1. And then when we plug this in, we get n times 0 times 1 times, or plus 1 times n minus 1 divided by 2, which is just n times n minus 1 divided by 2. But this sum would be different if we were trying to find the sum of the first n positive integers. Why is that? It's because a1 is different. Because here, for natural numbers, a1 would be 0, but for positive integers, a1 would be 1. So here are some exercises to do with the arithmetic sequence. Find the sum of the first n positive odd numbers.
You really love the positive odd numbers, huh?
Yeah. So there's two ways to solve this problem. One way is using the way that we just discussed, which is plugging it into this formula of Sn equals n times a1 plus k times n minus 1 divided by 2. Or we could just use induction, right? Which is what we did last lesson, I believe. So can anyone remember how we use induction to do this? We just compared the sum of n plus 1 with n minus 1, right? But over here, we can just plug it into the formula. So what's a1? a1 is just 1. And the common difference is 2, right? Thus, we have n times 1 plus 2 times n minus 1 divided by 2. That's our sum. But what's special about 2n minus 1 divided by 2? The 2's cancel. So it's just equal to 1 plus n minus 1, which is equal to n times n, which is equal to n squared. So now we found out that the sum of the first n positive integers is equal to n squared. Our positive odd numbers. So our next exercise is to find the sum of the first n positive even numbers. So again, we could either plug this into the formula or use induction. But if you plug it into the formula, it's much faster, in my opinion.
Mm. I
So
think it's
here's
also
some.
I think it's also worth noting that you could instead of using the formula, you could just factor out 2 from all the even numbers, right? And like something like 2 plus 4 plus 6 plus 8 plus plus 2n is equal to 2 times, if you factor the 2 out, it's 2 times 1 plus 2 plus 3 plus plus n. And if you recognize the sum of the triangle numbers to be n times n plus 1 over 2, you can pretty quickly get that the sum of the first n even numbers is just 2 times that. So you can just get it to n times n plus 1, like right away.
So because we had a1 equals 1 for the odd positive numbers, and we had a1 equals 2 for the positive even numbers, we get that the sums are different. Namely, we have n squared for the sum of the first n positive odd numbers, and we have n times n plus 1 for the sum of the first n positive even numbers. So this just goes to show how important a1 is.
Wait, if I might add something else as well. If you look at the difference between the even numbers and the sum of the first n even numbers and the sum of the first n odd numbers, you see that the sum of the first n even numbers is exactly n larger than the sum of the first n positive odd numbers, right? And I think that can be like kind of easily seen if you compare the terms, right? 2 is 1 larger than 1, 4 is 1 larger than 3, 6 is 1 larger than 5. So when you're adding the sum of the first n positive even numbers, you're basically just adding the first n positive odd numbers, but you're adding 1 to each of the terms. So you're adding n. So that's why because the sum of the first n odd numbers is n squared, for the even numbers it's n more. So it becomes n squared plus n. So that's like maybe another way you can figure out the even numbers just from the odd numbers, right? It's like the odd numbers plus like a little bit more, where a little bit more is n. Yeah.
So here's another exercise involving the arithmetic sum. So we have 3 stages of a pattern of matchsticks as shown below. Each stage requires a certain number of matchsticks. And how many matchsticks are required to make the figure in stage 100? Can anyone spot a pattern? Okay, let's just count how many we have in each stage. In stage 1, we have 4. So let's just write out the sequence. 4. Stage 2, we have 7. Stage 3, we have 10. So this seems like we have 3n plus 1, right? Because it increases by increments of 3 each time. And then it starts at 4. This can be further seen by every time we have a next stage, we add 1 matchstick on the top, we add 1 matchstick on the side, and we add 1 matchstick on the bottom. So it increases in even increments of 3. So the general formula would be 3n plus 1 for the total number of matchsticks required at each stage. So we have an equals 3n plus 1. And then we want to find the figure in stage 100. So we would just simply plug in 100. So we would know that a100 is 300 plus 1, which is 301. And then the second part of the question is, what stage would require 250 matchsticks? Does anyone have any ideas? So, okay, yeah, 83 is correct. So we're trying to find k such that ak equals 250, but we know that ak is the same thing as 3k plus 1. So we know that 3k equals 250 minus 1, which is 249. So k equals 83. And then the next sequence, the next series we'll cover will be the geometric series. In arithmetic sequences, we had a common arithmetic difference. And in geometric sequences, we have a common ratio. So we'll have a recursive formula of an plus 1 equals k times an. Or we can have an plus 1 divided by an equals k, which is a common ratio.
Yeah. Okay. Also, I'm not sure why. Yeah. Why do you use k for both the difference and the ratio?
It's usually r, but
yeah,
I just use
and the
k.
other one's normally d, right?
Yeah.
Well, I think it might be a bit confusing if using k for both. But
Okay, I'll just use r for this one.
yeah, r
So
for ratio.
the common ratio is denoted as r usually. And then before we had n plus 1 equals an plus d, the common difference. Okay. But now we have a common ratio. So given this common ratio, try to find a general formula for the nth term of a geometric sequence. Before we found the general formula for the nth term of an arithmetic sequence by just recursively doing an equals an minus 1 plus d, and then dot 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 until we have a2 equals a1 plus d. And then the technique we use here is called telescoping. where we add all of these equations together to get the sum from a2 to an plus 1 is equal to the sum from a1 to an plus n times the common difference. This is for arithmetic sequences, which ultimately gives us an plus 1 equals a1 plus d times n. So how would we go about finding the general form for the nth term of a geometric sequence? I'll give you guys 30 seconds to figure it out. So we can basically do the same thing, but then we don't need to cancel out terms. We can just sub in terms. So we know that an equals r times an minus 1, and then dot, 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 a2 equals a1 times r. So if we sub in a2 for the equation of a3, which is a3 equals r times a2, we find out that a3 is r squared times a1. And then we can keep doing this until we get the ultimate equation, which is an equals r to the n minus 1 times a1. So this is the general formula for the nth term of a geometric sequence. So that was predictiveness. And now we'll find the geometric sum. Chris will explain it.
Yes. Okay, so again, we're going to use the formula that we just derived. A sub n is equal to a sub 1 times like n minus 1 copies of r, right? So r to the power of n minus 1 times the first term. So the sum of, if we're trying to sum the first k terms, or should this be the first n terms?
Yeah, first
Yeah,
n.
yeah, I think there's a bit of a typo because you have the sum of a sub 1 plus a sub 2 up to a sub k.
Oh, okay, my bad.
Yeah, so if we want to find the sum of the first n terms, then we can just first of all rewrite everything in terms of the first term, right? So you can rewrite a sub 2 or a2 as a1 times r. You can rewrite a3 as a1 times r squared, and so on. And you can rewrite an as a1 times r to the n minus 1. And if you rewrite it all in terms of a1 and you factor out the a1, you get the sums a1 times in brackets 1 plus r squared plus r cubed plus dot 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 plus r to the n minus 1. And actually, when you see something of this form, right, like 1 plus x squared plus x cubed plus dot 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 plus x to the n, there's actually a pretty clean way of like kind of factorizing it or making it simpler. What you can do is, yeah, so we've got a hint here is multiply everything by r minus 1, and a lot of nice cancellation actually happens.
So essentially, all of these middle terms from r to the 1 to r to the n minus 1 all cancel out. So we're left with r to the n minus 1. So we know that this large expression of 1 plus r squared dot 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 plus r to the n minus 1 times r minus 1 equals r to the n minus 1.
Mm.
Or we can rearrange that equation to get that the sum is equal to r to the n minus 1 divided by r minus 1.
Well, you still have k at the bottom, by the way.
Oh yeah, I'll just change that.
Yeah. Also, I see that Alan says you can prove it with induction in your spare time. Alan really does seem to love his induction. I don't think it's necessary to prove this with induction. Like, I think it's like
You
off
could just
research.
prove it like by writing out the equations.
Yeah, yeah. I think like if you just list out the first, it comes it's, like obvious enough that like the things just cancel and you're left with. Also, it's well known anyway. You don't need to prove this, by the way. Like I'm pretty sure this factorization is very, very well known. You can just state it. It's okay.
So here are some exercises. Try to find the general formula for the sum of the first n terms of a geometric sequence with a common ratio of 1.
Damn. Okay.
So here, A1 is just A1, right? And then R equals 1. So we know that all the terms are equal to A1, which means the sum must be n times A1. It's quite intuitive,
But the
but
question
you
B
could,
is has a mistake in it. You probably want to stipulate that A1 is equal to 1 if you want the sum to approach 2.
oh yeah, wait. Okay. And then so let's try the second exercise. Prove that the sum of the first n terms of 1 plus it's 2 plus 4 plus dot 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 8 is just 2 to the n minus 1. So first we need to write out A1 equals 1. And the common ratio R is equal to 2, right? Plugging that into our formula that we discussed earlier, we have that is equal to R, A1 times R to the n, which is just 2 to the n, minus 1, divided by 2 minus 1. But 2 minus 1 is just 1, so it's dividing by 1. And then A1 is also 1. So we're just left with 2 to the n minus 1. You can see this in binary, because 2 to the n in binary is 1 followed by n zeros, and 2 to the n minus 1 is just a bunch of 1s, just n 1s. Suppose that the common ratio is 1/2 for some geometric series. Show that the sum of the first n terms as n approaches infinity approaches 2 times A1. I'll give you guys 30 seconds to try this. And Chris will explain.
Yeah. Yo, I might want to go quickly so we can get to the actual problems. Like this stuff is a bit boring.
Okay, time's up and Chris will explain.
Actually, wait, okay, just wait, Alan. Like, are we actually teaching the fourth part with characteristic roots?
Oh, we could just skip to the handout.
Okay, sure. Okay, anyway, um, what is this? Okay, so show that the sum of the first n terms is n approaches infinity approaches to A1. Okay, well, if we plug everything into our formula, as before, right? It's the first term times r to the like n minus 1 over r minus 1. Okay, what do we get? Well, n minus 1 as n approaches infinity. So you have r to the quote unquote infinity minus 1, right? But here r is equal to a half. So that clearly approaches 0, right? As you raise a half to, some number that's approaching infinity, a half to what's essentially infinity is just going to be like 0. Um, so you have 0 minus 1 over r minus 1, which is a half minus 1, which is negative 0.5. So it's minus 1 over minus 0.5. Remember, dividing by a half is the same as multiplying by 2. You know, it's that like common troll question, right? What's 40 divided by a half? It's 80. So 1 divided by half, you get 2, right? So you get 2a1. So what we mean by approaches is that this is what would happen if n equaled infinity, whatever that means, right? For a number to quote unquote equal infinity. But so okay, strictly speaking, I guess it's not equal to 0 minus 1. It's like the limit as n approaches infinity is 2 2 times a1. So the second question, right, is the sum ever actually equal to 2a1? Well, for it to actually equal to a1, we would need r to the power of n minus 1 to be equal to 0. But is it possible that a half to the power of some like integer is equal to 0? Well, I mean, you're multiplying a positive number by itself a bunch of times. Is that going to actually ever equal 0? While it can get arbitrarily close, right? It can get very, very small. It can get like infinitely small. It can't equal 0 because it's always going to be positive at the end, right? Which by definition is bigger than 0. So as long as you're raising this power of 2 to some positive integer, I'm sorry, this common ratio half, as long as you're raising it to some positive integer, I don't care how large, it's always going to stay positive. It's not going to equal 0. And if it doesn't equal 0, then it'll be like some small number minus 1 over negative 0.5, which is like a little bit less than 2. And it can get really close to 2, but it can't ever exactly equal 2. So the answer is no. No, it can't ever be 2 and 1. And here's a nice geometric interpretation of the previous exercise. You take some some square or some rectangle and you cut it in half, and that left half, that's our quote unquote first term of the sequence, and you keep slicing it in half. Well, you keep slicing the remaining area in half, and every time you do that, it's as if you're splitting the previous area in half, which is basically the same as saying you're taking a common ratio of a half and adding it to your current sum. And as you keep doing this, right, dividing the previous area in two and adding it to a new area, you see that the square gets more and more filled, but there'll always be a little gap in the corner, which is not yet filled, right? So you can keep doing this infinitely. But as long as it's not actually infinite and it's just some really, really large number, right? There'll be some really, really small gap still in the bottom right corner, which is not filled. And as long as it's not filled, that means that we'll never reach exactly the entire square or 2 times our first term. Well, our first term is like half the square, right? The left half of the square. That's our first term here. Yeah. So that's a nice geometric way of looking at it.
So this is the third property, which is sum convergence, where it states that if the common ratio is less than 1, then for some extremely large n, the term an will approach 0, which means that our sum will converge to some number. So as the sum of the first n terms of the geometric sequence is defined as the first term times the common ratio to the power of n divided by the common ratio minus 1. If the common ratio is less than 1, then if n approaches infinity, then r to the n will approach 0. And so we have that the sum as n approaches infinity will equal a1 times negative 1 over r minus 1, which is just equal to 1 over r minus 1. 1 minus over 1 minus r, sorry. So should we, okay, let's cover.
Actually, wait, can you go back to that slide? I have a few things to say about it. Okay, the first thing I want to say about it is that the common ratio can be negative, and as long as the absolute value of the ratio is less than 1, then it will converge, right? So something like negative 0.5 works as well. The second thing I want to like touch on is this little thing you wrote here. If after each iteration of the recursive formula, you're progressively left with a smaller and smaller term, and your term cannot become negative, then the term will quote unquote obviously approach 0. I don't think that's necessarily true because like just because it gets smaller, but it's not necessarily like getting more small every time, right? Like maybe if I have some sequence like 0.999 and then like 0.998 and then like 0.9979 and like 0.99 like 78 and then I can get smaller and smaller every time, but like it doesn't necessarily have to approach zero, right? Because we're dealing over the reals, it could taper off and um approach like 0.9 or something. In this case, it does approach zero because we are dealing with like a geometric series and or like successive powers, and that does like just bring it down towards zero. But I don't think in general you can say just because you're getting smaller and it's bounded by zero that it will definitely approach zero. Um, yeah. So just something to keep in mind.
So now we'll go over the telescoping series. So it's a basic technique within sequences where if you have the definition, an, which is the nth term of our series, equals bn minus bn plus 1 for some other series bn. And you have to find the sum a1 added all the way to an. Then you can simply expand these expressions to get b1 minus b2 plus b2 minus b3 plus dot 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 minus bn plus 1. And then we'll simplify this into b1 minus bn plus 1. This seems fairly obvious, but this is a fairly well-used technique and is very common in Olympiad problems. So a very famous example is to find the sum of 1/2 plus 1/6 plus all the way plus 1 divided by k times k minus 1. I'll give
We
you
start
guys,
with k equals 2 because if you try plugging in k equals 1, you get a bad division by 0.
yeah. So k is larger than or equal to 1. Oh no, 2. So I'll give you guys 30 seconds to try this problem.
30 seconds is kind of crazy.
Can anyone spot something special about these terms? About the term 1 over n times n minus 1. Feel free to type it into chat. Okay, so 1 divided by n times n minus 1 is simply equal to 1 divided by n minus 1 minus 1 divided by n. So why this true? We could just use subtraction of fractions to get this is equal to n minus n minus 1 divided by n minus 1 times n. And n minus n minus 1 is just 1. So we have this is simply equal to 1 divided by n times n minus 1. So now we seemingly have the sequence an equals bn minus bn plus 1 in the form of 1 over n minus 1 minus 1 over n. So we can just write an equals 1 over n times n minus 1 equals bn minus bn minus 1 minus bn, which is equal to 1 over n minus 1 minus 1 over n. But then as we established earlier, the sum from a1 to an is simply equal to b1 minus bn plus 1. So we have the sum is just 1. Oh wait, no, b1 minus b2 plus b2 minus b3 dot dot dot, and then we have bn minus 1 minus bn minus 1. Oh wait, it should be in front. Minus bn minus 1 plus bn minus 1. And finally, minus bn. So now we know that the sum of 1/2 plus 1/6 plus all the way to 1 over k times k minus 1 is equal to b1 minus bn. Oh, wait, sorry. So it's equal to b1 minus bn. But we have defined bk to be equal to 1 over k. So this is just equal to 1 over 1, or 1, minus 1 over k. So the final answer is that this large sum of fractions is equal to k minus 1 over k. So here's another exercise. Evaluate the sum of 1 divided by square root of 1 plus square root of 2, plus 1 divided by square root of 2 plus square root of 3, plus all the way to 1 divided by square root of 99 plus square root of 100. I'll give you guys 1 minute to try this problem, and Chris will explain it.
Okay, I think okay, that's fine. I'll give a hint after like maybe like 30 more seconds.
Wait, should I just give the hint?
Are you thinking of the same hint I'm thinking of?
Okay, I'll just give the hint. So whenever we have square roots on the denominator of a fraction, it's very hard to deal with directly, right?
Yeah.
So ideally, we want whole numbers as the denominators of these fractions. So how can we do that? Going from square roots, sum of square roots, to some type of whole number. What's an easy way to do that? That guarantees we can do this every time. Yeah, multiplying by the difference.
That's called like what, like rationalizing, right?
Yeah. So
What that means is that like if you have something like root a plus root b, if you multiply that by root a minus root b, on the top and the bottom, right, keeping the numerator and the denominator the same, then in the denominator you actually clear out the square roots, because root a plus root b times root a minus root b is just a minus b, right? So the denominator now becomes a rational number, which is nicer than irrational, right?
yeah. So basically, for the telescoping sequence to work, we must have them arithmetically canceling, right? But over here, these denominators are all like irrational, and they're all different because there's square root of 2s, there's square root of 3s, and there's also square root of 99. So obviously we need whole numbers on the bottom or rational numbers on the bottom. So note, if we multiply by the difference of these square roots, then we have square root of n plus 1 minus square root of n for each of these terms. And then if we sum them from a1 to a100, with an equals 1 divided by square root of n plus square root of m plus 1, we have square root of 2 minus square root of 1 plus square root of 3 minus square root of 2 plus all the way to square root of 100 minus square root of 99, which is just square root of 100 minus square root of 1, which is equal to 9. So now we'll go over the handout problems. Start from problem 1. It's a recap of the arithmetic sequence. I'll give you guys 30 seconds to try it. So we're given that the sum from A1 to A7 is equal to 70, right? And they form an arithmetic progression, which means they're part of some consecutive terms of an arithmetic sequence. So how can we write A2, A3, A4, dot, 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 to A7 in terms of A1? Can someone tell me in the chat? So before we define that the nth term of an arithmetic sequence or progression is an equals a1 plus n minus 1 times d, where d is the common difference. So here we can just plug in values of n. So we know that a2 equals a1 plus d, a3 equals a1 plus 2d, dot, 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 a7 equals a1 plus 6d. But what's the formula for the sum of a1 to a7? It's just Sn equals n times a1 plus n times n minus 1 times d divided by 2. Right? We covered this in the arithmetic sequence. So what's n and what's a1? Well, we're trying to find a1, right? Wait, are we? Okay, yeah. So we just assume a1 is equal to a1. We're not trying to find a1, we're trying to find d in terms of this, I think. Wait, no, I don't think I read the problem correctly. So let's just assume a1 equals 1. And we're trying to find d. So n equals 7. And n times n minus 1 divided by 2 is 7 times 6 divided by 2, which is 21. So we have the sum is equal to 7 times 1 plus 21d. But we also have that the sum is equal to 70, right? So we have that 70 equals 7 plus 21d. So 63 equals 21d. So d equals 3. And then let's move on to the next problem. So x, y, z are real numbers such that x squared, y squared, z squared forms an arithmetic progression. Prove that 1 over x plus y, 1 over y plus z, and 1 over z plus x also forms an arithmetic progression. I'll give you guys 2 minutes to try this problem, and then Chris will present the solution. Okay, your 2 minutes are up, and Chris will present the solution.
Hello. What time is it? 5:30. How much time? Okay, we have like 30 minutes left. Maybe give him like 1 more minute.
Okay, you guys can have 1 more minute.
Yeah, Reed, give me 1 more minute.
Oh, okay.
Nah, so good, so good.
Okay, that should be 1 minute.
Yeah, sure. I'm not sure if I'd like a super efficient solution, but it's okay. Okay, so let's start with, I guess, a fact about arithmetic sequences. Um, okay, A, B, and C are in arithmetic sequence if and only if. Well, okay, let's say A, B, C are ordered such that A is the smallest and C is the biggest, right? Then A, B, C are an arithmetic progression if and only if A plus C equals 2B. That's actually quite an interesting. I mean, it's sort of useful, right? So then arithmetic progression if and only if A plus C equals 2B, and you prove both directions, right? So if they are an arithmetic progression, then you have that like you can just easily check that A plus C equals 2B, right? And if A plus C equals 2B, then you can rearrange to get A minus, or to get, sorry, C minus B equals B minus A. And you see that their common difference is actually the same, right? This fact actually does also have an analog for geometric sequences. So for geometric sequences, A, B, and C are in geometric sequence if and only if AC equals B squared for similar reasons, right? Okay. So on to the problem now. So we have that x squared, y squared, and z squared are um sorry, x squared, y squared, and z squared are an arithmetic sequence. So using our fact, we know that x squared plus z squared equals 2 times y squared. Yes. And using our fact again, we would show that the other three terms are in an arithmetic sequence. So what we want to show is that um, two of those added together is double the third one. So what we're going to choose is we're going to choose the largest one and the smallest one, right? Oh, also, sorry, by the way, with log, I've ordered x less than y less than z. Yeah, so we want to show that 1 over x plus y plus 1 over y plus z equals 2 over x plus z, right? Wait, no, it should be x plus y plus x plus z. I think x plus z should be the one on the right. 1 over x plus y plus 1 over y plus z equals 2 over 2 x plus z. And that's because if x is less than y is less than z, then x plus y 1 over x plus y is going to be the largest, 1 over y plus z is going to be the smallest, and then 1 over x plus z is going to be the middle one. So using our fact that if we can show that this holds true, then we have also shown that these three are an arithmetic sequence or an arithmetic progression. And if you just expand it out, it just works. So yeah, you're done. It's just a bunch of algebra. Yeah, I'll leave that as an exercise. Oh, or if you expand, you have to use the fact that x squared plus z squared equals y squared, obviously, right? But if you use that, then the two sides will be equal. So very cool. Was there like an easier way of doing this, or?
You could just assume some arbitrary order
Mhm.
and then just do one of these terms minus another, and then it just works by
Oh
expanding.
yeah, sorry. Yeah, I mean, yeah, there's also that way of doing it, right?
Yeah.
Yeah, very cool, very
So that one contains some algebra that would take too long to type up.
cool.
So we'll just move on to the next problem because we covered the basic concept of solving that one. So the next problem is proof that there cannot be infinitely many long arithmetic sequences with only perfect squares. We'll give you guys 2 minutes for this one as well.
Yeah. Mercer has a question. Should this be done with algebra? Um, I mean, yeah, it is the algebra handout, yes. But you can, I mean, you can kind of like not use it. You can hand wave the algebra a little bit. Like I think there's a way of just like stating it. I mean, I guess if you want to rigorously do it, sure, you need algebra. But I think the main idea is somewhat just intuitive.
Okay, so for this problem, we have to first determine which direction the sequence goes. So does everyone know the trivial inequality that states that all perfect squares are positive and all real squares are more than or equal to 0? So they're all non-negative, which means that if we have an infinitely long arithmetic sequence or sequence of perfect squares, then will they be increasing or decreasing? Because they're arithmetic, which means they can only go in one direction. They can either only be the same, only increasing, or only decreasing. Can they only decrease and still be infinitely long? No, right? Because after an arbitrarily large n, we're guaranteed to reach 0.
I mean, it could just go zero. It could just go
Yeah,
below zero. The perfect squares.
perfect square.
Yeah, trivial
Yeah.
inequality, right?
And then, so we must have that, they must always be the same or larger than, or like constantly increasing. I think I made a typo, but then the arithmetic difference must be larger than 0 in this problem. So if we have different perfect squares each time, then we know that the sequence must be strictly increasing, i.e., we have that a1 is smaller than a2, smaller than dot dot dot, smaller than an. And there's some arbitrarily large number. So what does this tell us? I'll give you guys 30 seconds to think about this. Keep in mind that these perfect squares have a common difference. So as Chris stated earlier, we can rearrange this equation into the difference of an and an minus 1 is just the common difference. So let's call an bn squared. And let's call an minus 1 bn minus 1 squared. So we have a difference of squares. So we can factorize this into bn minus bn minus 1 times bn plus bn minus 1 equals d. However, this must be true for all bn, bi, right? So we have, this is equal to b1 or b2 minus b1 times b2 plus b1, which is also equal to the same thing for b3, and then it's the same thing for bi. But what does this mean? We know that an is strictly increasing, but an is the same thing as bn squared. So we know that bn must also be strictly increasing, assuming bi is positive. But this tells us that the sum of Bn plus Bn minus 1 must also be strictly increasing. But we have that the difference is always the same, right? Because it's an arithmetic progression. And if Bn plus Bn minus 1, which is one of these factors of this expression, is always increasing, then we know that the difference must always be decreasing. Right? So we can write this inequality now. We know that B1 or B2 minus B1 is larger than B3 minus B2, which is larger than dot 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 Bn minus Bn minus 1, which is larger than 0, because the common difference must always be positive since the sequence is strictly increasing. But here we run into an issue, right? Because B2 minus B1 is some constant C. All we know is that C is finite, but then the problem wants an infinitely long arithmetic sequence, right? But then we always have these strictly larger than inequality signs. And if C is finite, but is infinitely larger than 0, then we run into a contradiction. Because if you're finite, by definition, you're finitely larger than 0, or finitely smaller than 0, or equal to 0. But here we say that C is infinitely larger than 0, as there are infinitely many Bn's, Bi's, which means that C must be infinity, but then over here we have that C is finite. So we run into a contradiction. So now let's move on to problem 4.
Wait. So Alan has been spoiling too many of these handout problems, which you're gonna be doing, by yourself, right? Very unfortunate. So I might go teach you a little bit on like helper sequences or how to find formulas for more complicated sequences at least. I'm gonna pull up a Jamboard and send a link in the chat, and that's where I'll be doing my work since I don't want to be like typing up stuff on Google Slides, and also I don't have access to edit the Google Slides. Also, I tried finding, or actually, what I was trying to do is I was trying to create an easier problem, but unfortunately, the sequences I was trying to create weren't very good. So the example I use here might be a little bit complicated, but hopefully you guys get the general gist and can follow along. Okay. Um, okay, I posted in the chat. Okay, so we're gonna look at a sequence that's not an arithmetic or geometric sequence. Actually, I saw this problem from the problem of the day from like, a few weeks ago, so hopefully no one actually tried it. Okay, so we have a sequence, a sub n, where we have our first term. We're gonna call our first term a0. Okay, doesn't really matter. A0, we're gonna call it 1. Okay, and the defining characteristic of this sequence is an plus 1. So the next term of the sequence is defined purely in terms of an, but it's 34 times an plus 49 all over 25 an plus 36. And we're going to try find general formula for an. That's the problem. And you can try some small cases, right? You can plug in a0 into the formula, so you get a1 is equal to like 83 over 61 or something, and you keep going, but it's not really helpful, right? There is like it's hard to gain intuition on what the answer should be, right? So what we're gonna do is we're gonna play around with the formula a bit, and we're gonna try to like massage it into something that's a bit nicer, right? In particular, what we're gonna do is we're gonna like like algebraically manipulate the sequence a little bit and define some new sequences b of n and then later c of n, which would like which is gonna help us like solve the problem, right? Actually, just b of n I think is enough. Okay, so Um, okay, how we're gonna do this is we're gonna first of all, I don't really like if you have a look at our numerator and our denominator, I don't really like how there's like two a of n's, right? Kind of split across. I'm gonna try to get it so that there's only one term in which this term a n appears. So the way we're gonna do that is we're gonna try turn the numerator into something of the form k, some constant, times the denominator, plus some constant. Okay. So if I can get into this form, right? If I can transform it into this form, then I can simply I can just take the k out, right? Then I'll just take the k out and I'll have k plus c over the denominator. So the way we're going to transform it into this form is we're going to write it, well, we're going to take k to be equal to um 34 over 25. And like, I hope you see why, right? Because if k equals 34 plus 25, right, that's okay. Then it nicely cancels out with the 25 an to give us 34 an, right? So the only thing left to do now is to figure out what this value of c should be. So remember, this numerator up here is the same as this numerator up here. Yeah. So we need to find appropriate value of c that makes this numerator equal to this numerator. Okay, well, let's see what we have so far. So we have our 34n here, which corresponds to this, oh, sorry, 34an here, which corresponds to our 34an here. But now we also have this other term of like 34 times 36 over 25, which is kind of messy. So okay, that's not super good. But let's just okay, well, let's get rid of the C for now. Let's turn the C into well, we don't want this, right? So let's just quickly minus this 36 times 34 term out and then add back in our 45. I mean 49. So we have this 34an term corresponding to this 34an term. We have this 34 times 36 over 25, which we've canceled out with this 36 times 34 over 25. And we add our 49 back in, which corresponds to this 49. So this number up here, this expression is exactly the same as this expression. And this denominator is exactly the same as this denominator. So we've kind of like we've turned this whole expression into like this form, right? Um, so what that means is that we can now write this as, well, because we have 25an plus 36 here and 24an plus 36 over here, we can kind of cancel these out. And that just leaves us with 34 over 25. And then we're still left with this term over here, 36. Oh, can someone quickly calculate what this term actually is? I'm pretty sure it should be something nice. Um, might have to bring up my calculator, which is a little bit away.
97.96.
What is it? 97.96.
Oh, it's negative. Okay. It's 0.04, I think.
0.04. That's 1 over That's 1 over 25, yeah?
Yeah.
Okay, so this value here is just 1 over, well, this numerator here is just 1 over 25. So that's actually really nice, right? So that just gives us 34 over, oh, I just realized, okay, wait, the original problem actually had a negative sign in front here. I don't think that matters too much. I hope that doesn't matter too much. It's okay. Does that matter? It's really not, right? Okay, so you actually get, since this is just 1 over 25, the numerator up there, you get 1 over 25 times this. Cool. Probably going to move over to a new slide now, which is annoying because we have a lot of stuff on the slide. But okay, I'll just copy it down. So we've actually got it into a bit of a nicer form now, right? A n plus 1 equals 34 over, wait, what was it? 34 over 25 plus 1 over 25 times 25 an plus 36. And I say it's nicer because like before there were two ans, right? There were two spots where you had an, both here and here. But afterwards you have an in just one spot, like namely here. And okay, let's just multiply by 25 to get rid of these somewhat like ugly like 25 in the denominators, right? So now you have 25 an plus 1 equals 34 plus 1 over 25 an, oops, plus an plus 36. And what I'm going to do is I'm also going to just quickly subtract 34 from both sides. So, oh, okay, wait. Yeah, okay, never mind. The minus sign did have something to do with it. Sorry, okay, there's going to be a minus sign in front here, by the way. Whoops. I'll just quickly add it to everything. Minus, minus this, minus, minus, this is minus. Okay, yeah, so it's minus this. So it's minus that. And it's minus that. Whoops. Okay, sorry. Okay, so I'll add 34 to both sides now. And you have 25 an plus 1 plus 34 equals negative 1 over 25 an plus 36. And what you can really like recognize now is that since we've got it in this form, these two expressions actually look pretty similar, right? 25 an plus 1 plus 34 and 25 an plus 36. So what we'll do now is we'll define a helper sequence B of n. And we'll kind of define that to be like the sequence A of n, sorry, not just A of n, 25 A of n, well, A sub n, plus 34. Actually, sorry, I'll do plus 36. And this means that B of 0 is equal to, well, we said that A of 0, A0 was equal to 1. So we have that B0 is equal to just 61 then. So we start with 61. And we have that while using our like recursion up here, if we sub in bn equals 25 an plus 36, you get that on the left is bn plus 1. Sorry, bn plus 1 minus 2 equals minus 1, and that's just bn, right? Or in other words, bn plus 1 equals 2 minus 1 over bn. And this is like a much nicer recursion, like recursive formula, right? Compared to our original which was like an plus 1 equals minus 34an plus 49 over blah, 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 right? Which was quite complicated. So here, by defining this helper sequence, well, first algebraically manipulating our original one to get into a nicer form, and in defining this helper sequence, we get a much nicer formula here. And here, now you can start subbing in small terms, trying small cases. So what you might notice is that if you just start subbing in small cases and checking values, you get that b of well, obviously you have b of 0 equals b of 0, right? Which is just, sorry, I keep saying b of b sub, right? B0 is equal to b0, which we figured out was 61. um and then b1 is equal to, well, obviously just equal to 2 minus 1 over b0, which is 2b0 minus 1 over b0. Yeah. And you can keep going like this. So if you check b2, then b sub 2 is equal to okay, I'm not going to do the algebra because it is like a little bit long, but you do get 3 times b0 minus 2 over 2 times b0 minus 1. Here you can think of 1 b0 minus 0, I guess, right? So there's like a maybe a bit of a pattern you can see already. If you check b3, you get 4 b0 minus 3 over 3 b0 minus 2. So, okay, at this point, you might just conjecture an answer, right? So maybe you're thinking, bn equals n plus 1 b0 minus n over n b0 minus n minus 1. And the good thing about like sequences like this is that once you have a conjectured answer that looks like it holds and you're pretty sure it does hold, you can, like, you don't actually need to, like, you can just prove it holds by induction. Yeah, just check the base case, which we've checked, right? It works for the base cases. Then just sub into your formula, and if you just do the algebra, then it works for n plus 1 as well. So this is just our general formula for b of n, right? That's good. Oh, I guess I don't need to find. Okay, whatever. So once we have the formula for b of n, we can kind of just sub in a of n now, right? A, not a of n, a sub n, the sequence an, because we know that an is because we said that bn is 25 an plus 36. We have the equivalent relation that an is equal to bn minus 36 over 25, right? But we know that we have the closed form of bn, right? It's n plus 1 times, like, wait. Oh, sorry, n times 1 times b0, which was just 61, right? Minus n over n times 61 minus n minus 1. So therefore you have that a of n, a sub n, is equal to, like, the way of whatever. Wait. Okay, I can't copy paste that. I'll just delete this. It's equal to this minus 36 over 25. Okay, very cool. And yeah, that's should be the answer at least. I don't know if I didn't make any algebraic mistakes somewhere. We can maybe check this with a calculator if you want, but that's like the general premise, right? So, oh, cool. Anyway, seems like time's up. 6 p.m. now. Yeah, thanks for coming, everyone.
Thanks for coming. Your next lesson will be, I believe, next Saturday, and it will be on geometry.
Yes, taught by William Gong. Yes. Wow, I think everyone loves mine and Z. They all want to stay. Don't worry, guys. If you want to stay, I can give you an extra lesson on a pigeonhole problem. Oh, they all love mine and Z so much. So heartwarming.
Chris, I think you should give them your pigeonhole problem.
Oh, well, no way they're actually waiting for my problem. Um, don't worry, guys. Here's the problem. Okay. Okay. Two players, Chris and Alan. No, wait, no, shit. There's only one player. Um, one player plays a game. It's not even a game.